In this first example of demonstrating the power of two and or three force members and how it can simplify our problems, let's look at, in example 8.1, this case where we have this bar ABC. It's 3 meters long in entirety, and then we have two links. The link attached at A, it's inclined 60 degrees with respect to the horizontal, and then this link B that is inclined 30 degrees with respect to the horizontal. Now, the problem statement is key here in interpreting what's going on, because when you look at the structure itself, although it's implied, if you've seen a lot of these, that the links are attached with pins to each other, it's not immediately obvious, right? So it's a part a little bit that a lot of context here that you would say, oh yeah, they didn't draw the little dot that represented the pin, right? But the problem statement itself actually is also the giveaway that you're to interpret those as links, and therefore that they are pin connected, right? And so as soon as you see these members that are pin connected only and have no other forces applied, that's key, right? Only the two pins, that means those are two force members, and that will reduce the number of knowns significantly and make our life much easier, because we'll have only one unknown, right? It says two force members because it means that, okay, that member is either in pure tension or pure compression, but it also means that if we know the force at one end of the member, we know it at the other. Okay, so once again, how do we start our problems? Everybody, big chorus question, right? We always start with a free body diagram. We're going to start with the free body diagram here of ABC, and when we do that, of course, we're going to strip off everything else that's attached to it, apply the forces as appropriate. And now we start hitting the power of knowing that these are two force members, or these links, because at point A, if I pulled a pin in general, I would just have then the I'd have two things to put there, but since I know it's a two force member, I only show one force, kind of like it was a rope. It could go into compression, but I'm going to presume that it's shown in tension, and that would be the tension for the member at A. I could end up being wrong, so I'm going to actually turn that T into an F, call it F sub A. It's at an angle of 60 degrees with respect to the horizontal. And then over here at B, I'm going to do a similar thing and show a force that's going right along that line of action between the two connection points on the link. I'll call that F sub B. You might have just wanted to call it B if you wanted to, you could have. And here that's inclined 30 degrees with respect to the horizontal. And then finally we have the 3 kilonewton force sitting out here. But notice something kind of different and weird about this problem. We aren't given exactly what angle or orientation it's at. It's just drawn as alpha. Right? That is a correct free body diagram. It is complete. And notice now we go back. Maybe we should have read this to begin with. Right? Determine the reactions at A and B and the angle alpha of the tip force so that's at the tip out here, point C, of 3 kilonewtons. Oh, we don't know what the angle, how can that be? The applied force doesn't know a direction. But here's the key. We have one body, right? We've already identified that there were two force members involved, but we stripped them away and replaced them with a single unknown force. So on this body, count them up. I got 1, 2, 3 forces only, and that means the equilibrium equation is much simplified. And we can go speedily through this in the following kind of fashion, right? So identify a 3 force member, ABC, and the implication there, as we've talked about, is therefore the 3 kilonewton force F sub A and F sub B are concurrent. Right? And that matters a great deal, because if they're concurrent, then we know a lot of different interesting things. One, we could say we could represent this if we wanted to as we got forces at A. We've got, now I'm just sort of moving these all over the place, and I can kind of do that once I know that they're concurrent, right? Because there's no sum of moments left over now. And so now we've got then the 3 kilonewton force sitting there. I know angles of inclination of some of these, right? So now I could actually draw my FA as a 60-degree line. I've got FB at 30 degrees. Don't know its magnitude yet at all. All I know is that the 3 has to put this all into equilibrium. And so if I start thinking about how this all has to work, then what I could actually begin to do is think about the parallelogram construction of those two. The resultant of those two then is going to be like that, and that means that the buzzer, which is going off in the background, means that we got to speed things up here, right? That our 3 kilonewton force has to be equal and opposite of those two, and that tells us a whole lot of interesting information, right? Because we actually know the relative angle between FA and FB. That turns out to be 90 degrees. Oh wow, that actually told us all kinds of interesting things as soon as that becomes 90 degrees, just to add those two up. And so this diagonal turns out to have to be 3 kilonewtons, right? Very, very, very interesting, right? So, what does that tell us?